I want to talk about a concept that you probably got introduced to in your previous studies in calculus, and that's the idea of arc length. So if we have some sort of planar curve here, and we want to determine the distance that we travel from some starting point A to some ending point B, you can think of this little triangle to approximate that distance. So you have some sort of x distance, and you have some sort of y distance, and so the distance from A to B is the square root of the x distance plus the y distance. And that kind of gives us the general idea of how we approximate it. But just like we do in any calculus, you take those points from A to B and you dice them up really finely. And so each of those triangles shrinks and shrinks and shrinks until those distances along the line are actually what approximates it. And in our previous studies of calculus, we came up with these parametric equations, x of t and y of t. And we found that if you use that, by taking the time derivative or the derivative with respect to t of x and y, you ended up with a formula that took what is effectively this, right? We could think of that as sort of like dx dt and dy dt. And we were able to derive a formula for arc length. And again, that's what we saw before, but we're doing vector calculus now. So there's got to be a way to do this with vector calculus, and it turns out there is. So instead of parameterizing it with just x of t and y of t as ordered pairs, we can parameterize it with a vector valued function, where x of t and y of t are the I and j components respectively. And why is this helpful? Well, it's helpful because now we can, if we think about r prime, which is the velocity vector, if this were a position vector, then x prime and y prime are my I and j components of this, and the magnitude of that velocity vector is actually this quantity. So instead of writing the arc length in terms of these parameterized functions, we can write the arc length as the magnitude of the velocity vector from A to B. So integrating that dt from A to B. And why would I go to all that trouble? Well, because when we deal with vector valued functions, if we define them in terms of the vector instead of thinking about individual components, then that generalizes to vectors of any dimensionality. So this would apply to vector dimension 1, which isn't that useful, but we can also use it for vectors of dimension 3, and we end up with the exact same formula. So that's a very powerful way to generalize behaviors by defining them in terms of this methodology as opposed to this older methodology. And we're going to do some examples of putting this into practice.